All right, so we are back into OCaml Programming, correct, efficient, beautiful, aka CS3110. And it's the moment we've all been waiting for, which is functors. Okay? Functors. This is not the same thing as a functor in Haskell or category theory. It's its own thing in OCaml. Okay? And let's talk about some functors on April Fool's Day, as it is. You're starting to learn some web dev on Free Code Camp. Cool. Awesome. All right. So, Chapter 5, Section 9, Functors. The problem we were having in the previous section was that we wanted to add code to two different modules, but that code needed to be parameterized on the details of the module to which it was being added. It's that kind of parameterization that is enabled by an OCaml language feature called functors. Okay, interesting. Why the name functor? In category theory, a category contains morphisms, which are a generalization of functions as we know them, and a functor is a map between categories. Yeah. OCaml modules contain functions, and OCaml functors map from modules to modules. I know, that's what I always think when I say functions now, which is scary because it's not like functions is a new word to us purplish. And yet I still think functions describe the world. I don't get it. It's the brain. The brain is crazy. Hey, what's up, Gio? Welcome in. I know, Dylan. Classic Dylan brain F. Am I right? The world is so math. It's so math. Functions describe the world, Geo. Okay. All right. Okay, I've never seen this explanation before. Interesting. I have to think about this a little bit. So, in category theory, a category contains morphisms, yes, which are a generalization of functions as we know them, and a functor is map between categories, yes. Likewise, OCaml, like basically a functor, if I remember right, in category theory, a functor is kind of like a mappable. Like if you can map from one thing to another, that is a functor. There's a functor somewhere in there. I would usually think of it as the actual category, like the set being a functor, you could say, or objects of that set being a functor. But I don't know if that's the correct way to explain it. So since OCaml modules contain functions and OCaml functors map from modules to modules. Okay. I guess you could say that. Sure. All right, we'll take it. The name is unfortunately intimidating, but a functor is simply a function from modules to modules. The word function is in quotation marks in that sentence only because it's a kind of function that's not interchangeable with the rest of the functions we've already seen. OCaml's type system is stratified. Module values are distinct from other values. So functions from modules to modules cannot be written or used in the same way as functions from values to values. But conceptually, functors really are just functions. Here's a tiny example of a functor. Okay, module type x equals sig. So we have a module signature that has a single value x that has type int. Okay, and then our definition of that module. Oh no, okay. And then we have another module. This is the structure definition of that module. Is an incx. Marcel, thanks for the follow. I appreciate it. Welcome. So then we have a module incx, which takes any module that has type x, right, and returns a new module. Doesn't sound like a functor to me. I know. Were you I'm guessing you were here when I was reading through the his little explanation of why you would call it a functor. Like, I'm not like really good at category theory. You were here for half of it. I'm not really good at category theory, but like I don't know. I've gone a little bit through category theory for programmers. I forget the guy's name that did that one. And I did like a fair amount of Haskell five years ago or so, and learned things then. And I don't know. I don't like completely buy this, but that's okay. We just call it a functor, and we just know it's not the same thing as what we think of as a functor in category theory and Haskell. You have to do 4 clicks to sub with Prime now. I know. It's like they're de-incentive. I guess it's because it is like, it's not, you're not giving them new money. But yeah, thank you so much, Gio, for the Prime sub. Super appreciate it. Thank you for doing those 4 clicks. If a Cornell teacher says it's a functor, it's a functor. Classic appeal to authority, Juan Byte. You know that's a logical fallacy. Come on, man. You met that guy at a math conference. That's cool, Marcel. Yeah, I don't know. To be fair, he's not saying OCaml modules are functors. He is saying we use the name functor. He doesn't actually equate it. Hype train, holy moly, second one ever. Thanks for that Prime sub, Purplish. I super appreciate it. Pretty good. Let's go, hype train. Yeah, I mean it's interesting. It's maybe reminiscent of a functor, but you did it in 3. Man, optimizations. Okay, so we have module IncX, right? New module IncX, which takes any module of type X and returns a new module where X takes the X and M and does +1, right? Okay. I think that's all pretty obvious. We kind of get what that is. The functor's name is IncX. It essentially a function from modules to modules. As a function, it takes an input and produces an input. Its input is named M, and the type of its input is X. Yeah, they don't tell you when the Prime sub is ready. I forgot to use my Prime sub for like 3 months. The functor's name is IncX. Let's see. Its input is named M, and the type of its input is X. Its output is the structure that appears on the right-hand side of the equal sign. Sure, yes, obviously. Another way to think about IncX is that it's a parameterized structure. Okay. The parameter that it takes is named M and has type X. The structure itself has a single value named X in it. The value that X has will depend on the parameter M. Yes. Since functors are essentially functions, we apply them. Here's an example of applying IncX. Okay. Module A equals struct let X equals 0 end. Sure. And then we have A.X, which is int 0. Module B equals IncX A. So now we've applied A to IncX. And this is our new functored. It is a functored module. B.X. So obviously that now in B, the value of X is 1 because we've just taken the value inside of A and incremented it. And module C equals IncX B, which now makes it int 2. I don't hate this example of functors. I actually think that's really easy to follow, even though it's not like this is like perfectly like a real world scenario. It's pretty easy to follow. It's definitely easier than the OCaml manual's guide to functors, which I have read like 5 times and finally got it, but this is definitely easier to follow. Marcel says, Oh, it'll start with geo. Okay, so I think I understand what makes a functor as a functor. Functors are functions that map from a wrapped type A to another wrapped type B. Note A and B can be the same or different. The defining property for a functor f, according to Marcel here, is f to g, right, equals f of f to f of g, which I'm not sure that makes any sense here. Yes, I would agree with you. Yeah. So if we think about like a list, for instance, right? And we had like a list closure. Nice. Let's just get into some OCaml. Okay. So like if we had a list of ints, right? So in OCaml, that's something like this. Oh, did the stream die? Or is it just my preview of it? Stupid network errors. And the stream is dead. Okay. We love to see it. Come on. Come on. You can come back. You can come back. Should we switch to Wi-Fi? Hard to know. There it is. It's really thinking about it. Let's see if we came back or not. Sus. Unbelievable. Are we back? I can't tell if it's actually on. Let me check on mobile real quick. Live. And it's still dead. All right, I'm going to unplug. There we go. We should be back. Let's see. I see your guys' chats. Did the stream actually connect though, besides the chats? Okay, we're back. Stupid thing. Thanks, guys. Thanks for hanging out. The problem with FB is very often that the docs don't explain stuff in easy terms. That is pretty darn accurate, Dreadyfire. Yeah, your message broke my stream, Geo. And, you know, hiding prime subs broke my stream, and Hype Drink broke my stream. I think that's all the things that make sense. Okay, so what I was talking about, we were just talking about, oh yeah, what Marcel said. So Marcel said the defining property for a functor is this right here, right? So we'll just put this in a comment. Is we have f, and f maps to g equals f of f, which maps f to g, right? So if we took this, bad formatting aside, why does it love to do this to me? I just hate this so much. There's no reason for it to format this way. Like, why did you do this? Is it this? Like this is done. This is all done. Here, I'll give it a double semi. We'll give it a double semi so it stops bugging me. Okay. So basically this whole thing, right? So that's basically saying if we have a list of 1 and 2 and we apply a map function to it. Say it's just toString, right? So I think it's just toString in OCaml. So if we did like list.map toString 12. So this is kind of like a demonstration of map being a functor. And then the proof, right, is saying that if I map F to G inside of the F, it's the same thing as if I mapped it from the wrapper thing. That's the way I would think of the proof, whether that's a good explanation or not. So the point is that the F doesn't change. We still have a list at the end of this, right? We still have a list. Let's just say int toString at the end of it. The list hasn't changed, but our type went from int to string, from F to G. So like in terms of functors in OCaml, well, you can just take his example real quick. Let's just copy this for funsies. So if we took his module, his functor here, we have module type X. I mean, I guess if you define M as F in that statement, so say we have module and our first, so I guess, I mean, you could say modules are a functor. I don't know. It doesn't, I don't think it completely matches. I think that's really what it comes down to. Because if you have like, and I could be wrong, I don't have a math degree, I don't even have a CS degree, but like if you have module, it had module type X at the end of it, right? It's going to go to module type inc X. And I guess you could say this is the same. Not really, because I don't think this, does this even make sense? I don't know if that actually makes sense or not. I don't know. I'll let you guys figure that one out. I don't know if that's fair to say of the way that functors actually work in OCaml for us to consider that a module is a functor. Yeah, I don't know. I think it's orthogonal. I really do. I don't think it completely matches. The OCaml functors deal with inputs and outputs that are structs rather than primitives. Yeah, they do. But it still doesn't change the difference. Like, as in this example, I used ints and strings because it's easy, but I could have used record types or structs or whatever, right? Like, if I have type r equals x int, right? And then I have, I put a semicolon, hilarious. And then I have type, type s equals x stir. Like that doesn't really change anything. And if I said, you know, whatever, I don't feel like writing the function. But if we had a transformation, right? If we had a list of ours and transformed it, I don't think it'd be the same thing, but I don't know. But maybe you mean it in a different way, Gio. I don't know. Hey, Nightshade, what's up? I know, right? All right, one sec. Okay. All right, so I don't hate his example for functors. We were just kind of on a little rabbit trail about category theory, which I'm probably completely wrong about, which is fine. I'm wrong about all sorts of things. Each time we pass inkex a module, when we pass it the module bound to the name A, the input to inkex is struct let x equals 0 in. Functor inkex takes that input and produces an output. Struct let x equals a.x plus 1 end. Since a.x is 0, the result is struct let x equals 1 end. So B is bound to struct let x equals 1 end. Similarly, C ends up being bound to struct let x equals 2 end. Category theory is simple. Just put it into categories. It's not that hard. It's just sets of things. Unbelievable. Although the functor inkex returns a module that is quite similar to its input module, that need not be the case. In fact, a functor can return any module it likes. Perhaps something very different than its input structure. Yeah, so module addX takes a module of type X and defines an add function which adds m.x to y. Reasonable? I think we can skip through this until we get something more interesting. Note that the input module to addX contains a value named x, but the output module from addX does not. Yes. It's tempting to think that a functor is the same as extends in Java, and that the functor therefore extends the input module with new definitions while keeping the old definitions around too. The example above shows that is not the case. A functor is essentially just a function, and that function can return whatever the programmer wants. In fact, the output of the functor could be arbitrarily different than the input. Yeah. So if you want something more like extends in Java, you're probably looking for includes, as we went over yesterday. Functor syntax and semantics. In the functor syntax we've been using, module fms equals end, the type annotation. Oh, I missed a follow. Hey, Ryan, if you're still around, thanks for the follow. I appreciate it. The type annotation s and the parentheses around it, m has type of s, are required. The reason why is that OCaml needs the type information about s to be provided in order to do a good job with type inference for f itself. Yes. Much like functions, functors can be written anonymously. The following two syntaxes for functors are equivalent. Oh, interesting. No, I didn't. I missed that. I was busy this morning. I heard it's pretty wild. I don't know the details though. It is wild, yeah. Yeah, I heard it's pretty out there. It's cool that they went over it though. I'll have to catch a VOD. It's funny. I don't know if Antonio, when did this whole thing get exposed? Nightshade. 29th. Oh, okay. That makes sense. So then that's what this thing from Antonio Montero was in reference to. I didn't actually know about that. That's why it was, but this is a pretty good read by somebody that most people don't like, have never really heard of. He's kind of an unknown CS person. Ken Thompson, most people never heard of him. But it's pretty good. It's basically about the levels of obfuscation. Wait, what did you have installed via Brew? Oh, the XZ thing? I am probably silly for not even knowing what XZ is. XZ program. XZUtils is a set of free software command line lossless data compressors. Oh, okay. It's a compression library. Got it. Nice. So, what? I'm supposed to do this? Am I on the right version, guys? Is this what I'm supposed to do? Am I vulnerable right now? I've not been keeping up with this. I've just seen some of the subtweets about it. 5.6 and 5.6.1. Okay. So I'm good. Yeah. As no one who's used to my stream is shocked about, I have an older version than is vulnerable. Oh yeah. It is probably a max save since we have all of the old. It takes forever for them to actually put the new versions of Linux utils into Mac OS, right? Oh man, that's rough. Yeah, that's fair. That's fair. Um, it was in Brew, yeah, right. Yeah, I never remembered installing it, so I'm guessing this is just from. I do still have Brew. Pretty sure I don't have it installed via Brew. Oh, I do. I installed it probably another way. Okay. I don't know. It was probably a dependency of something else. But good thing I haven't run Brew Update in a while then. Maybe that's the real win. Oh, it only works on well, that is what I have. Yeah, this is an Intel based Mac. So I would be screwed. Um Oh, but then now upgrade will downgrade it. Yeah. Old and outdated for the win. It honestly is a lot of times, Purplish. I mean, I know we're like memeing, but like I never upgrade to the latest version of Mac OS. Like, are you kidding me? I wait till they have like 10 patch fixes and all that kind of stuff. And even then, I mean, I'm still on like 13, I think. Yep, I'm on 13. 13.6. Let's go. I know there's other problems, and sometimes that leads to vulnerabilities too, but I don't know. Sometimes not upgrading saves you a lot. Yeah, exactly. Exactly. Let other people beat test shit. All right. Good to know, Nightshade. Here we go. Did that work? No. Because oh good. Okay. Nice. uh Okay, so what were we talking about? Oh, there's a functor keyword. Nice. Okay. I didn't actually know about this. Much like functions, functors can be written anonymously. The following two syntaxes for functors are equivalent. You can say module F takes ms, so just kind of like your normal type annotation syntax, or you can use the functor keyword to create an anonymous functor, like how the fun keyword creates an anonymous function. And functors can be parameterized on multiple structures. It's kind of funny that like he said you can do this to create an anonymous functor, but then like what does that actually mean? Because he still gave the module a name. Like, in which way is this anonymous? I don't get it. You had to actually mod today in Prime's chat? Oh no. Terrible. Terrible. Um I will say, like, it is amazing, like when low level rated me yesterday, which was awesome, of course. He's done it twice, which is really sweet of him. But like, it's such a difference. Now, granted, there's a difference in audience, like size, but like 380 people came in and there were no need for mods. Everybody's just like super chill, really good about it. And I was impressed with that. Every time I see connecting to chat, I get scared. But no, we're still on. Okay. The second form uses the functor keyword to create an anonymous functor. Sure. And functors can be parameterized on multiple structures. Module FM1. Yeah. Of course, that's just syntactic sugar for a higher order functor that takes a structure as input and returns an anonymous functor. Sure. If you want to specify the output type of a functor, the syntax is again similar to functions. Yeah, then when prime raids all hell. Yeah, exactly. Like if prime ever raids me, like I'm gonna have to mod some people like right away. Oh man. Usual Russian. Thanks for the follow. I appreciate it. If you want to specify the output type of a functor, the syntax is again similar to functions. Module F, M, psi. So, as usual, it's also possible to write the output type. For some reason, I'm just not getting what he's on about, and maybe it's just something really simple. I get this, like what he's trying to say. Yeah, I said if prime raids. You have to convince prime to raid me, and then you'll get mod. If you want to specify the output type of a functor, the syntax is again similar to functions. Module F, M, psi, so. Oh, okay. It's just saying specifying the output type. What am I'm missing something here. I'm missing something important, I feel like. So module add x, mx equals struct. I get all that. Okay. So module f, m1, s1, same thing. All good. I guess I just wish he didn't do the ... dots and he just gave me a full freaking definition. And then I wouldn't be so confused. He might be able to pull some strings. Yeah. I mean, at least he follows me. It's very nice of him. And several of his shoutouts have been very, very helpful. But I'm entitled to a raid, aren't I? The cell is like, it's April Fool's Day. Of course you should raid me on April Fool's Day. I don't actually think he's still streaming though. All right. If you want to specify the output type of a functor, the syntax is again similar to functions. So let me just look at this. So module inc x mx equals struct let x. Oh, right, because you could have another module type, right? Okay, because we could have something like module type inc equals sig. I get it now. Val x int, right? I mean, technically inc x has the same signature as x. So that part is also a little interesting. I wonder if that works. Okay. So I was just getting confused. So we could definitely call it inc and we should be fine. LSP is fine with that. Now, I'm pretty sure we could actually call it X because the resulting module has the same signature as the original module. So it is kind of funny to think about that. I would say that's pretty uncommon, but it actually satisfies the module signature of X. Okay, so that's what he's on about, right? He rated someone he played Helldivers with today. That's awesome. Yeah, Nightshade, you know, he's kind of a big deal. He is a default Twitch mod. You have to send a special request to the company to not mod Nightshade on in your stream day one. As usual, it's also possible to write the output type annotation on the module expression. Yeah, at the end. Sure. Okay. That was good to read. I finally got it. It just took me a minute. A big dill. He is a big dill. Dill is excellent. Dill is it's definitely one of my favorite herbs. Fresh dill, pretty hard to beat. I mean, even dried dill is fine, but dill is very good. The simplest syntax for functor types is actually the same as for functions. Module type to module type. For example, x to add below is a functor type, and it works for the addX module we defined earlier in this section. Module type add has a function add. And we could say module check add x has the type x to add. Okay, cool. So similarly, we should be able to do something like module check inc x has type of x to x equals inc x. Yeah. Yeah, this dude doesn't even have a job. He just cooks, apparently. I think Nightshade's lying about his corporate job. Chopping fresh dill is hard. It's totally true. Canned new potatoes fried with dried dill and garlic powder. That actually sounds great. That actually sounds pretty good. Even if you are using canned potatoes. Functor type syntax becomes more complicated if the output module type is dependent upon the input module type. For example, suppose we wanted to create a functor that pairs up a value from one module with another module. He lives where the air is thin and the winters are cold. Module type T equals sig type T val xt, sure. And pair 1 takes a module of type T. Okay. Oh, I see. Because this pair actually doesn't specify, this is a generic, right? Type T is abstract actually and generic. Then pair 1 actually becomes an m.t and int, right? Tuple of m.t and int. Okay. The type of pair 1 turns out to be, we could also write module type p1 functor takes a module type t and returns a module that has a value of p, which is a tuple of m.t and int, equals functor mt. Okay, so let's compare these real quick. Like when, don't say back to top. I'm trying to freaking read. All right. It's supposed to be 70 this week. Yeah, no, this is insane. It was 78 yesterday. Now, granted, you're like, 10x my elevation, but still, that's very warm for March. Module type T. Okay, so we have like the way I usually see people write module types. Okay, understood. And then we have if we wanted to use the functor keyword. I can see why people don't use the functor keyword. Yeah, okay. Module type P1 is the type of a functor that takes an input module named M of module type T and returns an output module whose module type is given by the signature sig end. Inside the signature, the name M is in scope. That's why we can write m.t in it, thereby ensuring that the type of the first component of pair P is the type from the specific module M that is passed into pair 1, not any other module. For example, here are two different instantiations. Okay? Yes. So it's basically just saying the module that we put in can have a T of any type, right? Pretty obvious. It's still cold in Michigan. Yeah. Oh, you're going to Miami for a React conference? That's cool. It should be pretty nice in May. In Asheville. Should be pretty nice. Not too hot, not too cold. I mean, it won't be cold at all. I'm just hoping it won't be too hot based on how this year has been going. But, it's not high elevation, but it's at least in the mountains. It's a little bit cooler than other places. Pair 1 struct type T equals int. Yeah, okay. We already read that. Note the difference between int and char and the resulting module types. It's important that the output module type of pair 1 can distinguish those, and that's why M has to be nameable on the right-hand side of the arrow in P1. Yeah. Sure. Functor types are an example of an advanced programming language feature called dependent types. Meh. With which the type of an output is determined by the value of an input. I mean, he's right. He's right. Okay. That's different than the normal. I mean, that is true that is what a dependent type is, where it's the output value that's determined by the input value and the output type is independent of the input value. Okay. Yes. Dependent types enable type systems to express much more about the correctness of a program, but type checking and inference for dependent types is much more challenging. Practical dependent type systems are an active area of research. Perhaps someday they will become popular in mainstream languages. Maybe. The module type of a functor's actual argument need not be identical to the formal declared module type of the argument. It's fine to be a subtype. For example, it's fine to apply f below to either x or z. The extra item in z won't cause any difficulty. Uh-huh. I was thinking about something else. I wish Prophet was here because she would be the best person to ask this. But like, To me, it's that a module has been parameterized by another module. And I understand that the value, see, I don't think it's exactly fair to say that this is dependent type, because the value in one module is not actually what's determining the type of another module. It is it is actually the type of one module determining the value in another module. Let me think if that's true. I believe that is true. I mean, I guess I see. I guess there's a situation that's probably just because I'm a noob to functors, that you could use it like you would use a dependent type. But so far, I don't feel like he's really used it like you would use a dependent type. At this point, I would still think of this as a just a parameterized module. To me, this isn't that much different than what you could do, how you could parameterize something in another language. Now, the way that you actually accomplish it is different, but like the end result isn't that different. I guess that's what I'm saying. So I don't know. I don't know if I exactly think that calling it a dependent type here makes a lot of sense. I think that could give people the wrong idea of what dependent types are. I mean, he explained what a dependent type is, but I still think it kind of gives people the wrong idea. But that's kind of me. Functors cross into the too complicated of a solution to a problem to be useful territory for me. Yeah, I get that. I think you can make them really simple to where it makes sense. Like, I get where you would want to have them, but I think until you find the like use case for them, they're not going to make sense, right? It's kind of like defining your own trait in Rust or something, right? Type class in Haskell, right? Like, unless you have a really good reason to do that, most of the time you probably don't need to do that. So I don't know. That's the way I think of it. It's fine to apply f below to either x or z. The extra item in z won't cause any difficulty. Yeah, the module type of a functor's actual argument need not be identical to the formal declared module type of the argument. It's fine to be a subtype. Okay, right. So subtyping. So for instance, we have module f functor that takes a module that has an x that's an int, and it returns a y that is just that m.x, also an int. So module x equals struct let x equals 0 end. Yep. Module z equals struct let x equals 0, let z equals 0 end. Okay, so you can make an f of z is kind of the point. Malvi, thanks for the follow. I appreciate it. Welcome. You got third too. I mean, those internet points. Where are we at? I know Purplish is going to be like far ahead of everybody. We all know Purplish is going to be at the top. He's pretty darn good at clicking that first button. Yeah, this makes sense. Purplish and Nightshade. Internet fame. Okay. Lots of dancing gophers. You really only do it in my chat. Well, I feel really special now, Purplish. I feel really special. All right. 1 second here. Looks good. All right. Right. So we were going through this example. So we have module F. We finished going through it. Right. So because we have like subtyping, structural typing, OCaml is fine with us saying, hey, this module Z, which technically has an extra thing Z, we could still create an F out of that. We can still F that module all we want. All right. The map module. The standard library's map module implements a map, a binding from keys to values, using balanced binary trees. It uses functors in an important way. In this section, we study how to use it. You can see the implementation of that module on GitHub as well as its interface. The map module defines a functor make that creates a structure implementing a map over a particular type of keys. That type is the input structure to make. The type of that input structure is map.orderedType, which are types that support a compare operation. Okay, so module type ordered type equals sig type t val compare tt and end. Yeah, very good. The map module needs ordering because balanced binary trees need to be able to compare keys to determine whether one is greater than another. The compare function specification is the same as that for the comparison argument to list.sortUnique, which we previously discussed. The comparison should return 0 if two keys are equal. The comparison should return a strictly negative number if the first key is lesser than the second. Yep. So standard compare function, right? Does that specification seem a little strange? Does it seem hard to remember to return? Why not define a variant instead? Yeah, you could do a variant. But you know. The output of map.make supports all the usual operations we would expect from a dictionary. Module type S equals sig, type key, type AT, val empty, mem, add, find, etc. The type variable alpha is the type of values in the map, so any particular map module created by map.make can handle only one type of key, but is not restricted to any particular type of value. Okay, so any particular map module, yes, created by map.make, can handle only one type of key, yes, but is not restricted to any particular type of value. Okay. Let's get into this a little bit. See what the heck they're talking about. G Diaz, thanks for the follow. I appreciate it. Here's an example of using the map.make functor. Module int map equals map.make int. So module type is the type and functor is like function. Does the book hints on why they are not unified? I'm not sure if I know what you mean. Yeah, I don't know if you can answer that in a different way. I don't completely get it. If you show that output, you'll see the long module event map. The int module is part of the standard library. Conveniently, it already defines the two items required by ordered type, which are t and compare, with appropriate behaviors. The standard library also already defines modules for other primitive types, string, etc., that make it convenient to use any primitive type as a key. Now let's try out that map by mapping an int to a string. Open int map, let m1 add 1 empty. Okay? Yep. Find 1m1 gives us that. Mem 42m1 is bool find 42 M1 not found. Bindings M1 gives us the map as an A list, if you want to call it that. The same int map module allows us to map an int to a float. Let M2 equals add 1 dot empty. Oh, right. Because all we have is a module. This is just a module. That's the part I was missing. I was like, there's got to be, like, it's not going to be like a dynamic map on the other side. Like, the value can't be dynamic. It's still just 1. But that's because M2 is our actual map, right? Int map is just our module that says this is a module. This is a module that takes int keys, and then you're going to specify the value type. Okay. I missed that somehow. That's okay. But the keys must be int, not any other type. Yes. That's because the int map module was specifically created for keys that are integers and ordered accordingly. Again, order is crucial because the underlying data structure is a binary search tree, which requires key comparisons to figure out where in the tree to store a key. You can even see that in the standard library source code, of which the following is a lightly edited extract. Yep. So we have module make, which takes an ordered type. The ord.t is the type of our key. And then type alpha t is generic. And it is either a variant of empty or node of L alpha t, V, which is our key, D, which is our alpha, so I guess that's our actual value, is called D. Interesting. I guess D for data. I guess that's probably what it is. I'm used to thinking like V for value, but because you have a key and you have a value, that's not how it works in this case. V is key and D is data. Sure. And then we have our right, which is another alpha T. And then we have our H, which is our height of node. Of course, he explains it right after. I wasn't actually reading the comments. That's really funny. It literally explains it right after. I was just trying to make sense of it. Okay. Let empty equals empty. Let rec mem x equals and ... Sure. The key type is defined to be a synonym for the type T inside ord. Prime did the same thing. It's so funny. I do it a lot. And I mean, part of it is that like I also want to understand it without it all just being spoon-fed to me, right? But you know, it's also because I'm silly. Just a silly person. Except he popped up Vim and everything. Hilarious. The key type is defined to be a synonym for the type T inside ord, so key values are comparable using ord.compare. The mem function uses that to compare keys and decide whether to recurse on the left subtree or right subtree. Yep. Note how the implementer of map had a tricky problem to solve. Balanced binary search trees require a way to compare keys, but the implementer can't know in advance all the different types of keys that a client of the data structure will want to use, and each type of key might need its own comparison function. Although stdlib compare can be used to compare any two values of the same type, the result it returns isn't necessarily what a client will want. For example, it's not guaranteed to sort names in the way we wanted above. So the implementer of map used a functor to solve their problem. They parameterized on a module that bundles together the type of keys with a function that can be used to compare them. It's the client's responsibility to implement that module. Yeah. The Java Collections framework solves a similar problem in the TreeMap class, which has a constructor that takes a comparator. There, the client has the responsibility of implementing a class for comparisons rather than a structure. Though the language features are different, the idea is the same. And this, again, kind of goes back to the fact that that's why I wouldn't call a functor a dependent type, at least the way that it's being used here. Like, it's just a parameterized type. Because we could do the same thing in Java, we could do the same thing in Rust using traits. You have all those options, at least for this particular example. Maps with custom key types. When the type of a key becomes complicated, we might want to write our own custom comparison function. For example, suppose we want a map in which keys are records representing names, and in which names are sorted alphabetically by last name, then by first name. In the code below, we provide a module name that can compare records that way. Type name equals first string, last string. Module name equals struct, type t equals name. Let compare, first equals first, last equals last. Yeah. Match string.compare, yes, okay, C. Got it. Type name equals first string, last string, module name, sig type t equals name, val compare, name. Oh, just reading the type. The name module can be used as input to map.make because it satisfies the map.ordered type signature. Now we could use that map to associate names with birth years. Going straight for the Kardashians. Unbelievable. It's hilarious that middle-aged white guy professor is using the Kardashians as examples. Is he trying to be relevant? Burn this book. He's trying to be relevant because, you know, like, if you think about like the Venn diagram between people who think about and know about the Kardashians and people that want to learn OCaml, like, there's a pretty big overlap in the middle, don't you think? Pretty big overlap. I love it. Okay. Yes, so this is just instantiating last and first, and then we have name map empty, add k1, add k2, add k3, name map dot bindings nm. Note how the order of the keys in that list is not the same as the order in which we added them. The list is sorted according to the name.compare function we wrote. Several of the other functions in the map.s signature will also process map bindings in that sorted order. For example, map, fold, and iter. Yeah. Makes sense. How map uses module type constraints. In the standard library's map.mli interface, the specification for map.make is, okay, make takes an ordered type and returns an s with type key equals ord.t. Yes. The with constraint there is crucial. Recall that type constraints specialize a module type. Here, s with type key equals ord.t specializes s to expose the equality of s.key and ord.t In other words, the type of keys is the ordered type. You can see the effect of that sharing constraint by looking at the module type of our int map example from before. The sharing constraint is what caused the equals int.t to be present. Module int map say type key equals int.t, and the int module contains this line, type t equals int, yes. So int map.key equals int.t equals int, which is exactly why we're allowed to pass an int to the add and mim functions of int map. Without the type constraint, type key would have remained abstract. We can simulate that by adding a module type annotation of map.s, thereby resealing the module at that type without exposing the equality. Yeah, okay. So we went over this yesterday, but it makes sense. It's basically just a matter of like encapsulation and working around encapsulation if that's not what you want. Now it's impossible to add a binding to the map. Yeah. This kind of use case is why module type constraints are quite important in effective programming with the OCaml module system. Often it is necessary to specialize the output type of a functor to show a relationship between type in it and a type in one of the functor's inputs. Thinking through exactly what constraint is necessary can be challenging, though. Okay. Using functors. With map, we saw one use case for functors, producing a data structure that was parameterized on a client-provided ordering. Here are two more use cases. All right, so we went over map. Where are we at? 594. We're at the last section of functors. All right, I think I just need to stand up. All right, we're so good. Okay, it's stretching time though. Let's see. Don't hurt yourself again, Nightshade. Just be gentle, okay? Be gentle. Dang it, Nightshade. All right. Stretching that back. It's getting there. Okay. Hips and back. Completely stretched out. 100%. That's all the fitness I need for today. All right. Let's see. I have Slack notifications. Should I read them on stream? Okay, good deal. Just have to data fix something, but it can wait an hour or so. Two messages. Okay, test suites. Here we go. Here are two implementations of a stack. Let's see if we can judge his stack. All right. Module type stack that has a T, an empty, a push, a peek, and a pop. Sure. Module list stack Okay, module variant stack. That seems like three implementations of a stack, but that's fine. No, I mean there's two implementations in one signature. Suppose we wanted to write an OUnit test for list stack. Let test equals, sure. Unfortunately, to test a variant stack, we'd have to duplicate that code. And if we had another stack implementation, we'd have to duplicate the test for them too. That's not so horrible to contemplate if it's just one test case for a couple implementations. But if it's hundreds of tests for even a couple implementations, that's just too much duplication to be good software engineering. Please don't have hundreds of tests for your stack. I don't think that's probably necessary. Functors offer a better solution. We can write a functor that is parameterized on the stack implementation and produces the test for that implementation. Module stack tester takes a stack module and defines tests such as peak push x empty equals x, fun, assert equal 1 as empty push 1 peak. Assert equal 1. Wait, how does that work? How would that work for the variant stack? Why would that work? Push 1. Oh, I see. Because it would just narrow the type of E or S to an int. I'm a little confused, but it's fine. Let all tests list off flatten list stack tester dot test variant stack tester dot tests. Now, whenever we invent a new test, we add it to stack tester and it automatically gets run on both stack implementations. Nice. There is still some objectionable code duplication though, in that we have to write 2 lines of code per implementation. We can eliminate that duplication through the use of first class modules. Let stacks equals module list stack module variant stack. Sure. Let all tests. Let test m equals let module s equals val m stack, and let module t equals stack tester s in t dot tests. And let open list in stacks map tests flatten. Now it just suffices just to add the newest stack implementation to the stacks list. Okay. I guess tests is just in a different place. I'm not like 100% getting the whole push 1 on a variant stack, but I guess that's okay. I guess I'll survive. Because I feel like, I don't know, I guess we should just try this out real quick, because I'm not getting it. What should we do? I guess we'll just copy all of this, and we'll just put it all on UTOP. Where's UTOP? It looks like it's down here. Okay. So we have all of this variant stack malarkey. And all right, cool, man. Good luck. And let's just say, what would we have if we pushed 1? We'd have a variant stack of type int. Is basically what we would have. I mean, I don't 100% get, I guess the variant stack, the only difference is that 1 is an empty. Okay, I get it now. I think Where this example doesn't make a lot of sense is that you could imagine that you might have a stack where a value of int isn't valid. So like you would have to write a new test for that, but that's okay. I get his overall point still holds, I guess. Okay. Let's see. Extending multiple modules. Earlier, we tried to add a function of list to both list set and unique list set without having any duplicated code, but we didn't totally succeed. Now let's really do it right. The problem we had earlier was that we needed to parameterize the implementation of list on the add function and empty value in the set module. We can accomplish that parameterization with a functor. If we have a set that has empty mem_add elements, and then we have a set of list, right, that has an of list function. Notice how the functor in its body uses s.add. It takes the implementation of add from s and uses it to implement of list, and the same for empty, thus solving the exact problem we had before when we tried to use includes. When we apply set of list to our set implementations, we get modules containing an of list function for each implementation. Oh no, I can't read that. Nucky, thanks for the follow. I appreciate it. Yeah. So then if we say set of list for unique list set, we still get the of list function. Yeah. Understood. The functor has enabled the code reuse we couldn't get before. We now can implement a single of list function and from it derive implementations for two different sets, but that's the only function those two modules contain. Really what we want is a full set implementation that also contains the of list function. We can get that by combining includes with functors. Yeah. So this is kind of like the next step, right? So if you, for instance, wanted to even append some things onto the list module that with your own thing, but you also needed in that case to depend on something in the list module, well, you wouldn't exactly need a functor for that, right? You could still do it. But if you wanted to be generic over the list, right, then you could do it differently, right? Like for instance, if you just wanted to say anything that has an add and empty, we're going to accept and be able to add an of list function to. This would work. So yeah, that's a nice example. I like it. That functor takes a set as input and produces a module that contains everything from that set because of the include, as well as a new function of list. When we apply the functor, we get a very nice set module. Yeah, I think that's really nice. I'm trying to think. Is this something that I can do with Rust? Not really. Like I would have to go about it a completely different way, right? I would have to go about it a very different way. I would not be able to accomplish this as easily with Rust by any means. So this is kind of like a case that shows the power of higher order modules for sure. So it's a good example. Notice how the output structure records the fact that its type T is the same type as the type T in its input structure. They share it because of the include. Stepping back, what we just did bears more than a passing resemblance to class extension in Java. Yeah. We created a base module and extended its functionality with new code while preserving its old functionality. But whereas class extension necessitates that the newly extended class is a subtype of the old, and that it still has all the old functionality, OCaml functors are more fine-grained in what they can accomplish. We can choose whether they include the old functionality, and no subtyping relationships are necessarily involved. Moreover, the functor we wrote can be used to extend any set implementation with uplist, whereas class extension applies to just a single base class. There are ways of achieving something similar in object-oriented languages with mixins, which enable a class to reuse functionality from other classes without necessitating the complication of multiple inheritance. Sure. Very cool. Chapter 5. Here we go. Summary. The OCaml module system provides mechanisms for modularity that provide the similar capabilities and mechanisms you have seen in other languages, but seeing those mechanisms appear in different ways is hopefully helping you understand them better. OCaml abstract types and signatures, for example, provide a mechanism for abstraction that resembles Java visibility modifiers and interfaces. Seeing the same idea embodied in two different languages, but expressed in rather different ways, will hopefully help you recognize that idea when you encounter it in other languages in the future. Moreover, the idea that a type could be abstract is a foundational notion in programming language design. The OCaml module system makes that idea brutally apparent. Other languages like Java obscure it a bit by coupling it together with many other features all at once. There's a sense in which every Java class implicitly defines an abstract type. Actually, 4 abstract types that are related by subtyping, one for each visibility modifier, and all the methods of the class are functions on that abstract type. Functors are an advanced language feature in OCaml that might seem mysterious at first. If so, keep in mind, they're really just a kind of function that takes a structure as input and returns a structure as output. The reason they don't behave quite like normal OCaml functions is that structures are not first-class values in OCaml. You can't write regular functions that take a structure as input or return a structure as output, but functors can do just that. Functors and includes enable code reuse. The kinds of code reuse that object-oriented features enable can also be achieved with functors and include. Dramatic readings are the next redemption. That'd be pretty funny. Like where you give me an article to read and I read it dramatically. That's not to say that functors and includes are exactly equivalent to those object-oriented features. Some kinds of code reuse might be easier to achieve with one set of features than the other. One way to think about this might be that class extension is a very limited but very useful combination of functors and includes. Extending a class is like writing a functor that takes the base class as input, includes it, then adds new functions. But functors provide more general capability than class extension because they can compute arbitrary functions of their input structure rather than being limited to just certain kinds of extension. Perhaps the most important idea to get out of studying the OCaml module system is an appreciation for the aspects of modularity that transcend any given language, namespaces, abstraction, and code reuse. Having seen those ideas in a couple very different languages, you're equipped to recognize them more clearly in the next language you learn. Okay, very cool. I actually don't hate the way, like, I actually think his functor chapter, I think it's better than the OCaml manual for a beginner. I think it is a better explanation in general. The thing that the OCaml manual does better is that it's terser in that, well, I don't know if it's actually terser, but it's like all on one page. You find out what the module struct is, you find out what a module signature is, you see how they fit together, the different ways of defining them, and then you figure out how they're using a functor. But because his examples are a lot simpler, especially to start with, and even at the end, he doesn't even go into any particularly complex example, I think it actually made the functor chapter here better as an initial explanation. Yeah. Better for reference later than, yeah. I think if you already know what functors are, then maybe the OCaml manual is better. If you don't know what functors are, then this is probably better. All right, just check this message real quick. Okay, exercises. Complex synonym. Here's a module type for complex numbers which have a real and imaginary component. Okay. Module type complex sig equals sig. Has a 0 and an add. Sure. Improve that code by adding type t equals float star float. Show how the signature can be written more tersely because of the type synonym. You just add a t up here, and then you replace all the float star floats with t's. Boom. Done. Yeah. No, that's totally true, Purplish. Complex encapsulation. Here's a module for the module type from the previous exercise, like as in this same complex sig. Sure. So type t equals float star float. Let 0 is 0 tuple of 0 dots. Let add r1 i1 r2 i2 equals this. Investigate what happens if you make the following changes each independently and explain why any errors arise. Okay. I guess we can do this. I guess we need to, let's just do this all in the REPL. I'm not going to bother putting this in the source code. So we have module complex sig. We have this, which is complex. So at this point, I can say something like complex is 0, and it gives me that value, right? And I could say complex dot add complex dot 0 complex dot 0. Obviously, I could have just scoped that so it wasn't so annoying, and we'd get our 0 back. If we remove 0 from the structure, it doesn't really matter, right? If we remove add from the structure, it doesn't really matter. If we change 0 in the structure to let 0 equals 0, comma 0, we're going to get a type error because that's not a float. I don't see a point in doing any of these things. Okay. Well, it was a nice thought. It was a nice thought of doing that exercise. Big list queue. Use the following code to create list queue of exponentially increasing length, 10, 100, 1000. How big of a queue can you create before there's a noticeable delay? How big until there's a delay of at least 10 seconds? Okay. Sure. Uh-huh. So here's our function. So unbound module list queue, were we supposed to have a list queue in here? Is this something that he defined earlier and then didn't give it to us? Is the point that I'm supposed to implement? He shouldn't. No, I don't think he's asking me to implement list queue. That would be kind of silly. Is he thinking about queue? What does queue have? Queue has these things. Okay. This is annoying. And he doesn't explain how to do it. So I'm going to skip that one. Big batched queue. Use the following function to create batched queue of exponentially increasing length. Okay. Now how big of a queue can you create before there's a delay of at least 10 seconds? And again, this is like some thing that he's obviously defined earlier and then I don't actually have. Whatever. That's fine. We'll just skip those. Hopefully this doesn't continue, that he's expecting me to have like functions in the REPL that I don't already have. Queue efficiency. Compare the implementations of enqueue and list queue versus batch queue. Explain in your own words why the efficiency of list queue.enqueue is linear time and the length of the queue. Then explain why adding in elements to the queue takes time that is quadratic and in. Now consider batch queue and queue. Suppose that the queue is in a state where it has never had any elements dequeued. Explain in your own words why batched queue.enqueue is constant time. Then explain why adding in elements to the queue takes time that is linear and in. Okay. I don't think I care. I don't think I care, and it also would require me to actually know what the definition of enqueue is for these. I'm confused where this came from. Okay, so I don't get this part. It's fine. Binary search tree map. Write a module BST map that implements the map module type using a binary search tree type. Binary trees were covered earlier when we discussed algebraic data types. A binary search tree is a binary tree that obeys the following BST invariant. For any node n, every node in the left subtree of n has a value less than n's value, and every node in the right subtree of n has a value greater than n's value. Yep. Your node should store pairs of keys and values. The keys should be ordered by the BST invariant. Based on that invariant, you will always know whether to look left or right in a tree to find a particular tree. Okay, so this implements the map module type using a binary search tree type. So let's start by showing map. Really? Okay. Okay. Let me just think about this. This implements the map module type using a binary search tree type. Sure. So this says type key. I don't know if I understand this one either, unless his point is, I guess I could do an include. Maybe that's what he's asking me to do. I do an include, but I overwrite what the actual type T is. That's the only thing I can imagine doing here. It seems a little unclear and kind of big. I guess we could try. We could try it. If we say module BST map equals struct, why does Emacs do this to me? End. Really? This is what you're gonna do? Okay. Include map. I can't remember if I have to do like this or something, or if it just works. Let's just try this to start with. Oh, I capitalized module. That's funny. That's probably why it was weird about everything. I know. It was actually just it was a me problem, surprisingly. Okay, so let's just stick this into UTOP real quick. And by including map, my signature ends up being this whole thing. Map.ordered type, map.s, and map.make. Oh, it was the S, right. Okay, so I'm glad I did this because it's making it more simple. So the thing is that there has to be an ordered type. right? And then there has to be an S here. And then there's a map.make. And that's actually the map structure. So what is map.s? It's the big thing, I'm guessing. Yeah. So that's all these things. So the binary search tree instead of the binary tree, I probably won't actually implement it, but I want to at least understand what he's asking for. It's not map.order type. That's just our key. So that would just be like int. So that doesn't really matter. It would be like overwriting the type S, right? Now, I don't see how that would actually work though. I guess I mean, maybe I wasn't paying enough attention. I feel like this is like 10 times harder than any other exercise he's asked for with like zero context. All the other exercises were super obvious, and this is like not to me at all. All right, we're just gonna keep moving. Oh, what'd you say? Oh yeah. You start writing and then what? Yeah, no, it's fair. Like I feel like I have a pretty good grasp after reading all this, but and you know, having done some stuff, but like this whole thing, like I feel like doesn't exactly make a hell of a lot of sense to me. That implements the map module type using a binary search tree type. Like, what the hell is he even talking about? Yeah, the gap is too big right here. Write a module that implements the fraction module type below. Okay. Let's try to do this. Module type fraction equals sig type t. A fraction is a rational number p slash q, where q does not equal 0. Sure. Requires d does not equal 0, to float, to string, to int, to int. Yeah, so I would just say something like module f, which is a fraction, equals struct type t equals we're just going to do int star int and let make equals int that's funny, make equals x y. I guess this is to actually make the t. No, it's just to make the t. Okay. Let make xy equals x star y. Let numerator. Let me just do an end to make sure that we're like on the right track. And let's take out the type annotation so it doesn't think that I'm bad. Okay. It's just because of the type annotation. So we'll just add that at the end. Let numerator equals let numerator t equals oh no, that doesn't work, does it? It was shadow t. What should we call it? We'll just call it f, I guess. Usually function though. We'll call it fr. Sure. Is fr. Oh yeah, we can actually just do this, can't we? Can I just structure right here? No, that doesn't work. Yeah, it does. Yeah, it does. That works, doesn't it? I think this works. I forget. Does that actually work? Let's just try it real quick. Let's just say make 1, 2 and numerator. I think that's right. Okay. The expression has type OKHP, but an expression was expected of type AB. Sure. Yeah. So that didn't work. So let's just say this is FR, and this is, I forgot how tuple access works then. Is it just FR.0? Am I like crazy right now? Let T equals 1 star 2. Oh my God. Not what I meant to do. 1 comma 2. There we go. T0? No. How do you get the first element of a tuple without destructuring? I forget. Tuples and OCaml. Oh, this is actually probably a good place to go. First, gosh. For some reason I just couldn't get there. Thanks. All right, and it's second, right? Yeah. Okay. So this makes this easy because the numerator is actually going to be first and denominator equals second. And then let to string it just has to return a string. I'm guessing that there's not like a built-in toString for tuples. That way you just kind of have to do it yourself. I guess toString anyway shouldn't be done that way, so that's fine. So instead we're just going to say, what's concat? First and I know I'm messing something up here, which is this int.toString. Yeah, we're lisping it right now. That's what we're doing. Int.toString. And by lisping it, I mean yeah. I think that works. Shall we test it? F.toString T. Oh, me. That works. Okay. Just making sure. All right. Let to float equals I mean, I guess I could do this way too, where I say function and I could put them here and I could say XY I guess we could call them ND. ND. And this would just be n/d. And then we would need a 2 float though. Is it int.2 float? Yeah. Something like this should work. Might help if I didn't say 2 float. Okay, that should work. And that would actually make this function, I think, a little bit nicer. What do we think? Function syntax, little destructuring. And then instead of having to do this, we say n. And instead of having to do this, we say d. Get rid of that. We should be able to get rid of this, but I'm not like 100% on that. It just depends on order of operation. Because it's right associative, I think that would actually be fine. This should work just fine. Yeah. Okay. That's a little bit nicer. Okay. What else do we have? Add. This is what, to actually do fraction addition and multiply. I don't know if I want to do those. I don't feel like thinking through fraction addition and multiplication. I mean, the addition's fine if we're not doing any sort of reducing, but I guess we can do the add part. Add takes 1 and 2, and then we're going to say match fr1, fr2 with n1, d1, comma, n2, d2. And then we have a new thing, a new tuple, n1 plus n2, and d1 plus d2. Okay, that wasn't very hard, was it? Yeah, that looks right. And I mean, arguably, we could put that all on one line, and I don't think that's really too much. Maybe a little too much there. We could put this on one line since it only has one guard. It's kind of a lot going on, but not too much. I guess multiplication of fractions is not hard, right? Am I crazy in thinking that half times half equals fourth? You just multiply. If we don't have to think about, again, if we're not thinking about reduction and all those kinds of stupid rules, it's not that hard. I probably should have actually just copied this and saved myself the typing. n1 star n2, d1 star d2. Okay. And finally, we can say module f has type fraction. Nope. D1 and D2 has to be equal to work like that in add. Oh yeah, you're absolutely right. That's why I didn't want to do it. I knew there was a reason I didn't want to do add, and I couldn't remember because I just wasn't thinking about basic math. It's hilarious. Okay. Well, even though the add doesn't work. Hey Abdi, how's it going, man? How have you been? So what's our actual error? Type pokeHP is not compatible with type T pokeHP star pokeHP. Uh-huh. Why not? So make takes int and returns T. Yeah, this is annoying. Busy? I feel that. Let's just put it in the REPL and see if we get anything better. Hey, thanks for that Prime sub. Super appreciate it. Okay. So obviously our add is broken, and that's fine. Okay, so it's our make that doesn't match. And is that just because our type alias? It could just be our type alias. Okay, let's try this and see if it changes anything. Nope. It's not because of the type alias. Oh, int to int. Did I just type that wrong? Oh my gosh. Classic. Just classic, guys. Unbelievable. Not unbelievable at all, of course. It's fine. It's fine. We know it works. Difference between constructing a tuple. I wrote the tuple type instead of writing tuple construction, right? Yeah, I do that a lot. Nice. Oh yeah, GG had it. GG had it. But you know, I had to cook, right? I had to figure it out. All right. Fraction reduce. Modify your implementation of fraction to ensure these invariants hold for every value v of type t that is returned from make, add, and mul. V is in reduced form. The denominator of v is positive. I don't remember having a v. Was there even a v? Oh, okay. No, they're just giving the value returned. The denominator of v is positive. Yeah, I don't actually care about this. This has nothing to do with OCaml. Let me just put here that I don't care about finding the common denominator. Add is broken because I'm lazy. All right. Make car map. To create a standard library map, we first have to use the map.makeFunctor to produce a module that is specialized for the type of keys we want. Type the following in utop. Okay, let's just make sure this is a 1 star, but we'll just try it anyway. Find the values of empty, add, and remove in that signature. Okay, we're going to. I don't see it. Empty. Alpha T. I don't feel like doing this. I don't think this is going to help us at all. All right. I mean, okay, so an empty returns the value, right, of alpha t. That's fine. Oh no, it just returns an empty map. See, this is why I should do it. It returns the empty map. Okay. We know how that works. Okay. Because type T is actually the result of map.make car T with alpha as the parameter. What's the other one you wanted me to explain? Add. Add takes a key, which is a car, a alpha, which is the type of our value. So let's say it was like car to int or something like that. And then return and the map, and then returns the map. That's updated with that added. Okay. And remove is going to be pretty darn similar to that. Where is it? Why don't I see remove? Did I already go past it? I did. Remove takes a key and a map and returns the map with that removed. Yeah. Cool. That was not completely helpful for me to go through. Car ordered or char ordered, depending on your preference. The map.make functor requires its input module to match the map.order type signature. Look at that signature as well as the signature for the char module. Yep. Explain in your own words why we were allowed to pass char as an argument to map.make. Yeah, that's because char has a compare function. Yep. I don't need to do this. I think using the map is pretty straightforward. I think this is just understanding how an immutable map works. I don't think that's required. Exercise, date, order. Okay, we might get into this. I actually have to go. I lost track of time. I've got to go. So let's find somebody to rate.